All right. So everybody who's in the back right now, if you guys want to come in, squeeze in a little bit, I definitely think we have a little bit more room for you guys. Also, we are streaming on YouTube, so if you guys don't want to be crammed in here, you guys can also watch us on YouTube. But definitely, guys, come in. All right. So we'll get started shortly. We have a lot of content to cover today. Question? It's on our link tree on GatorAI. So if you go on our Instagram and then go to our link tree, you can find our stream. All right. So we will start right now. So introductions. So hi, my name is Alvin Wong. I'm the education lead here at GatorAI. I currently work in 3 research labs. All of them use machine learning. The first one is a transportation one, another one is a Parkinson's one, and the third one is an NLP lab. I'm also working for Verifone as a machine learning engineer intern in their IPPD program, and we're doing fraud detection. I have today Kartik, Karthuria, and Siobhan, who are also ML lecturers, so if you guys could stand up and wave to the crowd, that'd be great. They're going to be also lecturing for some of the other lectures, and we have Srinikath, but he is unable to make it today, unfortunately. So just some introductions. So what does this lecture series hope to cover? So we hope to cover beginner machine learning concepts to develop a strong foundational knowledge with a focus on deep learning and neural networks. And we're really mean beginner and overview. We want to teach you the logic and the mathematics behind why these models work, but maybe we're not going to go so much into how to code these models because we want you guys to figure that out outside of this course. And we want to focus on really the background here. So I have a list of the 5 first lectures, the topics I'll be covering. So what is AI and ML? Linear regression, logistic regression, optimization, and gradient descent, feed-forward neural networks, and you get the idea. Throughout the rest of the lectures after that, we'll be covering different types of neural networks, how to train them, and how to test on them. For contact, you can reach out to us on Discord, email, or Instagram. All of our information is on our link tree, and our link tree is on our Instagram, obviously. So yeah. Resources, we're going to have additional resources for this lecture series in a Google Drive that will be shared on our link tree after this lecture is done. We're also going to be posting these streams on YouTube so you guys can see them after we're finished. All right, enough introductions. What is artificial intelligence? So actually, I wanted to pose this as a question to you guys. So does anybody have an idea of what actually is artificial intelligence, and could they give me a brief definition? Any hands? Yeah.
Artificial intelligence at its basic is just having input, sending input data to anything, and then it being able to make a choice based off that input data.
All right. I like that answer. Does anybody else have any sense? So yeah?
Just weights.
Just weights? All right. Just weights. Yeah?
To improve its output over time.
To improve its output over time. I like those answers, but what I'm looking for is that artificial intelligence, by definition, is actually very broad. So we have the definition here, the theory and development of computer systems able to perform tasks that normally require human intelligence. So what does that mean, human intelligence, right? So some examples that sometimes people often provide is visual, perception, decision-making, speech recognition, right? Some of the things we heard in the answers. All right, actually there's a very broad definition of what artificial intelligence can actually be, but I want to contrast this with an opposing effect called the AI effect, which is basically a phenomenon where either the definition of AI or the concept of intelligence has been adjusted to exclude systems that have been mastered or normalized. So what do I mean by this is basically every single time a concept is well understood or we interact it every day, we kind of stop considering it artificial intelligence and we kind of just say, oh, that's just computation, to quote Rodney Brooks, who is an Australian roboticist. So some of the things that have been considered AI in the past and are not AI really today is speech to text, text recognition, face detection, and ELIZA. I actually want to tell the story of ELIZA. ELIZA was developed as an NLP bot. So it's basically a chatbot. But it was a chatbot in a different way in which it stored a large amount of predetermined responses to somebody, and based on rejects rules, it would actually respond back to that person. And so the story goes for ELIZA is that it was actually able to fool multiple people into believing that it was an actual person when really it was just a bank of sentences that it was responding with. So we can kind of see how the definition of AI is very broad, and it depends on the perceived difficulty of a problem. And as soon as it's normalized, it's often labeled as computation. This doesn't apply to all of artificial intelligence, and we'll see this with machine learning, but it's a good idea to keep in mind. So what is machine learning? Can I get some answers again? Anybody have an idea? Yes?
Machine learning is like when you have a series of inputs and you train a machine to give a set of outputs.
To give a set of outputs, nice. I like that. Yes?
Like kind of building on that, like you train with like resonant patterns and things like that.
Yeah.
And then like essentially like identify them as
I like that too. All right, we got some technical issues.
How do you do this, bro?
Kushagra told me that you click screen record and it
Kushagra
works.
here?
Kushagra is not here.
Bro, where'd he go?
You click screen record and apparently it works.
Oh.
All right.
Okay.
Let me click video capture device. Does that work? I don't think that works. Check the stream. All right, we're gonna keep going, but we do have some technical difficulty that we might need to work on. All right, so those are good definitions. I like those definitions. So here are some additional definitions that we have. So machine learning is the study of computer algorithms that improve automatically through experience. And the other one, you can read that off the slide if you want. So what separates really machine learning from artificial intelligence and regular computation? So machine learning does not equal artificial intelligence. A lot of people kind of treat them as the same, but that's not true. Machine learning is a subset of artificial intelligence. So what it actually is machine learning is just utilizing previous data to create models to make predictions, right? And depending on the data we give the model, these predictions will be different. The output is not determined by the input and the algorithm only. It's determined by what data you use to train your model, right? So some types of machine learning that people are familiar with is supervised learning, right? You have essentially a set of labeled data, and you're labeling it and you're basically just training a model to map the inputs to the labels, right? So some classic examples are regression and classification. Regression is essentially where you're predicting a value, and classification is where you're predicting a class for an input. We have unsupervised learning, where you're training a model using a data set that has no labels. What you're looking here is for your model to find structures or patterns in the data that you can use. So some things would be clustering, dimensionality reduction, anomaly detection. You guys might not be familiar with these kinds of models, but that's okay. We'll explain them throughout the rest of this series. Semi-supervised learning is where you have a data set that has a small amount of labeled data and you have a large amount of unlabeled data. So you might use the labeled data to create more synthetic labeled data and then use that to train your final model. Some examples would be fraud detection and image classification. And then we have reinforcement learning, where you're training a model to interact with an environment by taking actions and receiving rewards. So some examples would be like game bots and autonomous driving. So here is the scikit-learn cheat sheet, as people would say, of how to choose which model or which kind of machine learning you want to use. It's good to have kind of in the back of your head, but not to follow it too closely. But it just gives you a brief overview of how you can follow this pipeline to essentially choose which model you want. Another way to look at machine learning is through the machine learning pipeline. So essentially, it's how do I use machine learning to solve a problem, right? So first off, you identify a problem you want to solve, right? So often you want to predict a value or a class, right? You might want to predict how many three-pointers is LeBron James going to make in the game tonight for my bet, right? Or you might want to predict a class, something simple like I have a set of images of apples and bananas. How do I classify an image as an apple versus a banana, right? So after you've identified your problem, you want to collect and pre-process some data that is predictive of the problem, right? So you could go to the supermarket and take a bunch of pictures of apples and bananas, or you could go online and just download a bunch of images of apples and bananas. And then you train a model on your collected data and you test your model's performance, right? So this is a good way to think about how do I approach a problem with machine learning and how do I make sure that I'm successful with it, right? Also, if any of you guys have any questions, just feel free to stop me and I'll answer them as we go, right? So let's start with an example of an ML pipeline, right? How do we determine the price of a house based on features of the house, right? So first we have our problem, we've identified it here. Now we're gonna do some data collection. We could search online for a data set containing house prices and other information on something like Kaggle, or we could go to Zillow. We could even search up houses and make our own data set, collect their price and other information that we want, right? we then have to do data pre-processing. So this is a very important part, is you want to define your features. And a feature is an individual measurable property that is given as input to your model and what you use to train your model. So we could extract the features ourselves, like I said before, go to Zillow, we extract all of the features, but also we want features that are extremely predictive of a price of a house. So what might be some features that are predictive of a house price? Does anybody have any thoughts? Yes?
Large backyard, balcony.
Large backyard, all right. I want to remind that it has to be a measurable value. So how would you measure the size of your backyard? Square footage, good.
Number of bedrooms and bathrooms.
Number of bedrooms and bathrooms, good. Anybody else? Yes? Average prices of the houses around that house. That's a good one. Yes?
Square footage of the house.
Square footage of the house. Any other features that we think would be predictive? Yes?
Age of the house.
Age of the house. That's very good. All right. So you guys have a lot of good features, right, that we've collected now. So now we're going to do some feature engineering with these features that we've collected, right? So feature engineering is a key part of the data processing pipeline. It's basically transforming the data that we've collected into features that can be used by the model, right? So I'm going to say for the example, we take the features of square footage and years built, and we're going to place them in our data set represented by a matrix, right? So if we have n examples, right, n examples of the square footage and the year built, then we can represent the data set as an n by 2 matrix, and the data and the prices can be represented by a vector of length n. And so we're going to define a vector for simplicity in terms here as just an ordered collection of numbers, and then we're going to define a matrix here as an ordered collection of vectors, right? I'm sure later when you guys take linear algebra, your professor will give you the whole spiel about how you can't define a vector unless you first define a vector space, and then you have to go through all of that. But we can, cut it close enough by saying it's just an ordered collection of numbers and stuff like that, right? So we have the data matrix X and our result vector Y, which represents our data set, right? So we let Xi be the features and Yi be the value for each example I, and you can see here in the red highlighted boxes, the first example, our first data point has 2,951 square feet, was built in 1980, and costs around $170,000, right? So we have a data matrix X, and we have a result vector Y, right? And we have them represented in our matrix and vector forms. So how do we train a model to essentially optimize this, or how do we train a model to use the data set to predict the Y values, right? So we can first we can do some data analysis and look into our data, right? So let's say here on the right-hand side, I've plotted all the prices of the house I find in my data set. And I look at it and I see, wow, it looks a little bit like a 2D plane in 3D space, right? So I'm going to say that I want a model that predicts a house price using a 2D plane, right? So recall the equation of a 2D plane is W1 x1 plus W2 x2 plus B, right, equals y hat. So here we have an equation that can represent any plane in 3D space, right? And we want to use this as technically our model, right, to predict the price of our house, right? And this is essentially the backbone of machine learning, is that we can actually conceptualize each model as a mathematical function that takes in inputs, has a set of parameters that defines the function, and returns an output that we want, right? So in this case, x1 is our square footage, x2 is the year built, y hat is the price. We could use more features, right? We could extend and generalize this to where we have m set of features, and then you can imagine that the graph on the right-hand side would look a lot more complicated, but it doesn't change what we're doing here, right? We have a set of weights that determines how the square footage and year built impact the price of a house. All right, so we want to train the model that uses this equation, right? So our parameters are W1, W2, B, right, which represent the weights and the intercept respectively. We have our inputs x1, x2, and our output is y hat, right? So like I said, we think of this as a function, right, we think of this as a function of f of theta, where theta is our parameters, right? And we can see that our function is determined uniquely by the parameters that we have chosen, right? If we change the parameters, we can get any 2D plane that we want that represents this function. So now that we know what kind of equation we want to have and what our parameters are, how do we choose the best parameters of theta given by our data set, right? So what does it mean to actually have the best parameters W1, W2, and B? Does anybody know what it means without reading the slides? No cheating. Yes.
You have a set of parameters that minimizes the loss function.
All right, that's a good question. That's a good answer. Yeah. Anybody else? What does it mean? Yes.
Is it like the parameters that are like, I guess that makes the most sense, like with the least outliers?
The parameters that makes the most sense with the least outliers. Could you expand on that maybe?
Yeah, so like, for example, you'd say, okay, if the house is in Florida, that's one parameter, but
Yeah.
the square feet might be a more important parameter. So like, the fact that the house is in Florida might have less weight than if it had like more or less
Yeah.
square feet.
Okay, I like that. Anybody else? What does the best parameters mean? Yes.
The parameters that minimize the loss function.
All right, yeah, that was the previous answer we got. You guys obviously have some background knowledge on that. But essentially, yes, right? So we want our 2D plane to provide the most accurate price when given the input, which is our features of the square footage and the year built, right? So what you can think about this is actually an optimization problem at its core. If you guys are familiar, right? You guys took calculus, you know about optimization problems. So what we can actually do is we can define a loss function, right? Which is a function that measures how far off our model is, which in this case is a 2D plane, how far our model's predictions are from the true values in the data set. And that's represented by this function here, L of theta, right? And it's actually just the average of the residuals from our 2D plane, right? So what do I mean by that? So if you look at our next slide on the right-hand side, you see our graph. So you see the residuals. Let's say our 2D plane is what we have chosen to be our model, right? But the actual prices for some houses might vary from our model's predictions, right? So the difference in what our model predicts and the real price of the house are called the residuals in this case, right? And I have some residuals up there. It's not all of them, obviously, but black represents that our model is underestimating the price of the house, and the red lines are going below the 2D plane, which means our model is overestimating the price of the house based on its features, right? So we want to minimize our loss function, right? The function that measures the amount of error that we have, right, of our model on the trading data. And we define this as theta star, right, which is the arguments of theta that minimizes our loss function, right? So you can see here how our loss function is really just measuring f theta of xi. So that's what our model predicts, right? Minus yi, which is the actual true price of the house. And we're just summing up all of these residuals, and then we're averaging out, right? Because we have n examples. So we're getting the average loss from this loss function, all right? And this is called the mean absolute error. It's not what's usually used, but it provides a better understanding, especially for people who are new to this. So the loss function is calculated as the average of the length of the residuals, right? And so how do we use our model now to predict the price of a house given unseen inputs, right? So we use our model, or formula in this case, right, as a function, and we pass in the inputs and we get our output. So for example, this plane is represented by the equation 120x1 plus 3000x2 plus yada yada. So we just place in our features, right, which is square footage and year built, and we'll get out our predicted price. And we'll learn about how to actually get to these parameters later on, but that's kind of a bit more out of topic or beyond the scope of this first lecture that we're having, right? So let's say we've got our model now. We magically somehow came up with the optimal parameters to solve our problem, right? How do we evaluate our model now, right? So we want to use a metric to assess our model, right? So for classification, this is mostly accuracy, but for regression, when we're predicting a value, we want something like mean squared error or mean absolute error. And mean absolute error was the loss function that we were using before. So we want to evaluate our model using data that the model has not already been trained on, that the model has not already seen. Does anybody know why this might be the case? We don't want to use data that the model has been trained on to test it. Yes?
So it doesn't overfit.
So it doesn't overfit? Yes?
Well, if you're giving a model that the data that the model's already been trained on is the answer, it's kind of like, here, take a test, but you already know all the answers.
All right, I like
It's
that.
not really gonna get
I like
you.
that answer. All right. Any other answers? No? All right. But yeah, that basically summed it up. So, we wouldn't be necessarily surprised if the model we trained our data on perform very well on the model it has already seen, right? The model knows what the data has been beforehand, so it can really, in a term, fit to it very well and kind of predict the prices, right? What we want to do is we want a separate test set for evaluation of our model. And on the right-hand side, you can see the kind of average or a very normal split for train, validation, and test, right? So we do training on around 70% of our data set maybe, right? And then we're going to use validation and we're going to tune maybe some hyperparameters. And hyperparameters we'll talk about later in the course. And then we have the test set, right, which is where we want to test our model. And these are some common train, validation, and test splits. Essentially, as you go down, as you have more and more data, you want to leave more and more for the training because you have enough data already for your validation and test split. But if you have less data, you want to focus more on testing and validation because, yes, question.
Just to clarify, so validation is refining the parameters and making sure that, you said hyperparameters.
Yeah, so hyperparameters are parameters that should not be defined by the data, but are defined by the machine learning engineer who's designing the model, right? So we'll learn a little bit more about hyperparameters, but essentially hyperparameters can determine the impact of your model, but if you overfit them to your data, then essentially what happens is that your model is doing good for essentially no correct reason, right? The hyperparameters are not connected to the actual trained data. So yeah, so if there were to be some takeaways from this, the machine learning pipeline, right? So we have 4 steps, right? We have analyzing the problem, right? So we have to define our problem. We have to ask ourselves even, do we need machine learning? And can machine learning solve this, right? Because a lot of times you will have an issue or a problem, right, where you have a data set, and you actually do not need a machine learning model to solve it. You can really just write some really good algorithms that take your input and map it to your output, and you don't need a machine learning model. And sometimes people always try to use ML, but it's not always needed. And it can definitely result in high costs, especially if you're building a very large model. The computation, the time, and the effort is very expensive, right? And then, of course, yes, question.
So that note that you just made, does that mean that hypothetically for the example you got, you could use like a Taylor series or something instead of like actual machine learning algorithm?
Yeah, you could do that in a sense. I mean, linear regression in a sense is also just like mathematics at its core, right? You're just defining the linear combination, right, of variables. But yeah, you can also like. What I mean to say is that every ML model is really conceptualized as a mathematical function. So right, so you can yes, in a sense, yes, yeah. All right, so the second step is collecting and pre-processing the data, right? So you have to think about getting your data, how much data do you need for your model, cleaning your data. Sometimes your data will be very noisy. There's going to be a lot of missing variables, right? You want to visualize your data, right? So what we did before, right? When we plotted all of the data points and we saw the structure of the data, when we were seeing the structure of that data, that's what led us to choose our 2D plane as our model for the house prices, right? So feature engineering and then choosing the feature we want, and also choosing useful features, right? A lot of features will actually just add a lot of noise. They won't be very useful in your predictions, and they can actually make your model perform worse if you provide those features in the first place. So training a model on your collected data, right? Overview, so what is your task, right? What assumptions are you making about the data structure? And what you will find is that a lot of models, like the one we just made, we actually assumed made a lot of assumptions about the structure of the data. We essentially assumed that all of the features of square footage and price had a linear effect on the price of a house. And that might not be true, right? There might not be a linear weight that corresponds the square footage to the price of a house, right? So we can also talk about different model types you want to choose and tuning hyperparameters again, right? That is also in this. And then finally, when you're testing your model, you have to figure out how do you want to test your model? What metrics do you want to use? What metrics are really useful? Some are not so useful. What's the baseline accuracy of your task? And this is more so for classification. But let's say you have a fraud detection algorithm or a fraud detection machine learning algorithm, right? I could create a very naive model that always predicts that a transaction is not fraudulent, right? And that's, a very naive model, but it actually performs super well. I get a 99% accuracy. And the reason for this is not because my naive model is very good actually at determining whether a transaction is fraudulent or not, but it's actually because the baseline accuracy for a fraudulent transaction is so low. The majority of transactions are actually legitimate, right? So even with this naive model, I can get a very high accuracy. So you have to be careful when you're testing your model and seeing your accuracy and your metrics, and you have to compare it to what is the actual baseline true positive rate, right? And of course, we have underfitting and overfitting, which we'll talk about more in depth in the rest of this course. And so, another final takeaway is, if there's anything you should take away from this lecture, is at its core, machine learning is an optimization problem, right? We conceptualize each machine learning model as a function taking inputs and resulting in a certain amount of outputs, right? Where the parameters define the model that we're using, right? And so machine learning is essentially trying to narrow down the functions that we are testing for in a way that we can actually find a good enough function to map the inputs to the outputs, right? You can imagine there's an infinite amount of functions from any set of inputs to an output, and it's just extremely difficult to find unless you take some assumptions, right? So we want to find that best function, and we do find that best function by defining a loss function, right? And the loss function measures the error, right? A model's predictions are from the true target. I put error in brackets here because oftentimes it's a very abstract value, what it means to have the loss function, what it actually predicts, right? And so essentially, we try to find the parameters that minimizes our loss function, that minimizes our error, so that we can find the parameters for the best model. And we want our model to make accurate predictions, right, on new unseen data, and that's when it generalizes, right? So that's very important why we have that test split, that train validation test split, because when you're splitting on the data, you actually get a good enough idea of how your model is going to perform in the real world on data that has not been trained on yet before, right? Of course, we can also think of machine learning as the pipeline, right? So how do I use machine learning to solve the problem? I can follow a set of steps, and it provides me a good enough pathway to make predictions on some type of value or some type of classification issue. But that's about it from me. And I have the sign-in page at the very end here. Please sign in if you guys haven't. But yeah, thank you very much. I'm also going to be up here for questions. So if you guys want to come up and ask me something, if you guys want to ask one of the ML lecturers here anything, please feel free to. Thank you so much for your time, everybody.
Thank you.